Hello, my name is Adam Hines, and today I'll be presenting our paper titled VPRTempo, a fast, temporally encoded spiking neural network for visual place recognition. This work is a collaborative effort with Peter Stratton, Michael Milford, and Tobias Fischer at the QUT Centre for Robotics. Visual place recognition, or VPR for short, is a critical function in robotic localization, involving the matching of input query images to a database of recognized places, which can be challenging due to the dynamic nature of environments that are influenced by changes such as seasons or the weather. Traditional and state-of-the-art methods to perform VPR tasks often employ convolutional neural networks, trained on large datasets for generalized feature extraction. While these methods perform well, their ability to be utilized in resource-limited compute scenarios for real-time deployment is limited due to the complexity of these models. As an alternative strategy, spiking neural networks have garnered interest for VPR tasks thanks to their low latency and energy efficiency, but have ultimately seen limited use. Recently, a highly biorealistic spiking neural network was developed for VPR with comparable performance to state-of-the-art systems, however, was unable to be deployed due to the complexity of modeling biological neurons. We therefore introduce a novel spiking neural network for VPR that uses a temporal coding scheme where spike timing is a function of pixel intensity, allowing a single spike to convey up to 255 times more information than in rate-encoded systems. Using a simple 2x2 example, we can see how pixel intensity through different inputs can determine the temporal code of a spike within a time step. This approach substantially reduced the necessary spikes required to represent the same pixel data, improving spike efficiency by over 100%. Our network's architecture is composed of 3 layers: the input layer aligned with the image dimensions, sparsely connected to a feature layer, and a fully connected output layer, where each neuron signifies a unique place. To improve both scalability and precision, we partitioned our network into expert modules, each responsible for non-overlapping sections of traversal datasets. To demonstrate the training regime, we first take raw input images, reduce the dimensionality down to 28 by 28 pixels, and perform patch normalization to the pixel intensities, which helps keep our system lightweight and robust to variations in lighting conditions across reference and query images. Then, the training phase involves 2 pivotal steps. Initially, connection weights between the input and feature layers are updated through spike timing dependent plasticity, or STDP, learning rules. This is where the unique temporal coding scheme of our spiking network comes into play, as the intensity or amplitude of the spike across the layers can easily have their respective timings determined. Subsequently, we apply one hot encoding and a delta learning rule to train the feature to the output layer, to force each output neuron to learn one particular place in the reference dataset. By forcing a spike in the output neuron, network weights across the feature to output layer can effectively be learned through the same STDP learning rules. During deployment, we integrate all the layers, input the query images, and identify the neuron with the highest amplitude in the output layer as the corresponding match to the reference database. Compared with a state-of-the-art spiking neural network system for VPR, our system learned an equivalent number of places in approximately 16% and less than 1% of the time when trained on CPU or GPU hardware, respectively. This increase in training speed highlights the potential for VPRTempo to be deployed to learn large-scale datasets, with our system capable of learning up to 27,000 places in under 10 minutes and queryable in hundreds of hertz when deployed on GPU hardware. When comparing against state-of-the-art systems for overall performance, we see that our network performs comparably for precision at 100% recall across two standard VPR datasets, Nordland and Oxford RobotCar, with substantially reduced training and inference times, highlighting its suitability for deployment in real-time compute scenarios. Future work will focus on developing this system to be able to perform real-time VPR with incoming camera streams, with the potential to become capable of online learning. We will also be exploring the transition to neuromorphic hardware, where spiking neural networks can be deployed for highly energy efficient and low latency operations. In conclusion, we have presented VPRTempo, the first temporally encoded spiking neural network for VPR, a real-time capable solution that is able to be deployed on robotic platforms and perform comparably to modern state-of-the-art systems in place matching accuracy. Thank you for listening.